In this video, we're going to be discussing the 2K fractional factorial design, which is a really cool extension of the 2K factorial design that we were talking about in the last chapter. Fractional factorials are factorials where we literally run a fraction of the runs that would be required for running the full design. Typically, these fractional factorials are run based on the 2K design. Now this should make a lot of sense because as we get a large number of factors, which is one of the benefits of 2K, is that we can assess a large number of factors very quickly all together in the same design. But when we actually get those large number of factors, enough factors to be interesting, the size of the design, that is the number of runs that we have to do, grows very quickly. In fact, it's an exponential growth. When our goal is just screening factors, it's tough in this particular case because we have so many different runs, but all that we're looking for is just to find a few of the factors that really stand out with large effects. And it seems like a waste that we're doing so many runs to find just this simple thing. We might have a whole bunch of different variables that we're looking for, and again, these designs tend to be implemented when we really don't know which of the independent variables may be related to the dependent variable. So we're kind of trying to test everything very quickly and very efficiently, and that's where these 2K designs enter. Now, because we're trying to use the least amount of runs possible, these tend to be run as an unreplicated factorial design. That is, there's no little n, there's no replications in here. Though sometimes you'll see these run with center points. This is a more advanced feature that we're not going to discuss in this class, but I highly recommend you check it out on your textbook. Alright, so it seems kind of weird, at least it did to me when I was a student and first learning about it. The thought that we're going to run a design that may need a certain sample size to run, at least from what we said previously, and we're literally going to cut that sample size in half or in a quarter or in an eighth. So why do these fractional designs work? The first idea is the sparsity of effects principle. So we might have a whole ton of different factors. Remember, we're testing kind of the whole kit and caboodle, everything in the kitchen sink, throwing everything possible into this model to really figure out which of the independent variables relate to the dependent variable. But we're assuming that only a few are important, these few outstanding factors that actually relate to the dependent variable. That's our goal, is just to find these few that are sticking out. So what we're looking for is these few that are important, and we're assuming that they are going to stick out. Now, think about this. Whenever we run a full factorial design, we're looking at all of the possible interactions among all the possible factors. And again, in many cases, we really don't care. We're just looking for the few important pieces. So what we're going to end up doing is selecting the runs that we choose to keep in such a way such that each of those runs gives the most information possible about the factors of interest. Now, what's really interesting is, based on our design, if we design this in a systematic way, which we're going to teach you in this lesson, we're going to be able to contain the full factorial with a fewer number of factors. It's kind of a really interesting idea. Another piece of this leading into the sequential experimentation is that if we design this in a systematic way, we can flip the system back around. So let's say we ran it with half the runs. We can run the other half of the runs, and that would give us a full factorial design, again, just by flipping the system by which we chose our runs around. Of course, in sequential experimentation, just what I said, we could always turn these into a full factorial just by running the opposite. But we can add runs to the fractional factorial. So as we're looking at these main effects and lower order interactions, these main effects are going to be confounded with some other things, but we could add runs to resolve any ambiguities that the main effects are confounded with. So as it turns out that we need to really dive in depth on a couple of variables that seem to be important, but we're not quite sure, we can use sequential experimentation to add runs in a very efficient way. So when we're looking at, we'll start by looking at the 1/2 fraction of the 2 to the k design. 2 to the 3. Now note this is a 1/2 fraction. We literally are going to run half of the runs. We're going to take the 2k runs required for the full factorial design, and we're going to divide it by 2. Note that in dividing by 2 or dividing by 4, dividing by 8, dividing by different powers of 2, in our 2k, that's just subtracting from the exponent. So that's why you see this denoted in the opening slide as 2 to the k minus p. P is going to be the number of cuts we're going to make. In a 1/2, p would be 1. In a 1/4, p would be 2. In a 1/8, p would be 3. Now, when we make these cuts, trying to figure out which of the values we should keep, it can be done in a couple of different ways. One of my favorites is to create what's called a defining relation, which is what we're going to talk about later. So that is pretty much you pick one of these terms and you're going to use the plus sign to that term to figure out what to keep. So in this case, the defining relation is going to be the identity is ABC. So I and ABC. We're going to figure out where ABC has the plus signs, and these are the runs that we're going to use. We're going to run one with, remember what these mean. A lower level A means this run has a high level of A and a low level of B and C, which aren't shown. This lowercase b means that we're going to do a run with a low level of A, a high level of B, and a low level of C. This lowercase c means we're going to do a run with a low level of A, a low level of B, and a high level of C, and so on. ABC is high levels of A, B, and C. So we're going to use these 4 specific runs, and that's how we're going to select which runs we're going to use. So everything where A, B, C is positive according to this defining relation. There's another way that we can do this too that we'll talk about in a second. Now we can look at this, and what becomes interesting is when we use at the defining relation, or we can use the opposite of the defining relation. In fact, these are the 2 ways that we could come up with the full fractional design. Think about the defining relation here, and then the opposite. So if we did one run here, and then we did the opposite down here, that would give us our full factorial design. So in this particular case, we have our defining relation as the positive A, B, and C. So the interesting thing that happens though when we just run with half of the runs is that some of the elements are going to start to be repeated. So A, right now we would find the effect of A by adding A, ABC, AB, AC together, and then subtracting B, C, BC, and the one where all of the levels are at the low level, that 1 value. That's how we would find the effect of A. But now, if we just kept the top half, and I want you to visually kind of draw a line down the middle here. I'm not accurate enough to draw it myself. But if we just kept the top half, the first 4 of these runs, plus, minus, minus, plus, actually appears somewhere else on this table. It appears with BC, plus, minus, minus, plus. Now this is showing this visually, but the idea is that A is the exact same thing as BC. So the equation we would use for looking at the effect of A is the exact same equation we would look at the effect for BC. Now this is called confounding or aliasing, and that means that we can't tease out the effect of A and the effect of BC. Now this is the bad part about these types of designs, is they combine effects, and this is the cost of doing fewer runs, is that we can't tease out these differences. The theoretical idea behind why this is okay is that, well, the interaction probably isn't really there, so anything that we see is just the effect of A, and of course in a more advanced way we can tease that out even further. So when we look at aliasing, if we looked at each of those columns and we try to figure out for the top 4 which are the same, we would say the A column is the same as the BC column, and I encourage you to rewind the video and check these out. A is the same as BC, B is the same as AC, and C is the same as AB. So all of these main effects are the same as a 2-factor interaction for each one of these values, and again you can rewind to go back to that table or draw out your own table and check it out. Now, though we could look at the table to find these, the aliasing can also be found from this defining relation. So we used this ABC to pick out which runs we were going to keep, but this ABC can tell us what the aliasing structure is going to look like too. So if I took A and I multiplied it by the identity, or ABC in this case, then A times ABC, well, remember when we have two A's, they kind of cancel out, so I'd just be left with BC. Same thing with B and AC. So I take B, I multiply it by ABC. I've got two B's, they kind of cancel out, and I'm left with AC. I take C, I multiply by ABC. The two C's cancel out, and I'm left with AB. So that gives us our defining structure here. And you'll note that all this is a formulaic way of looking at that full table, saying if I just keep the positives for ABC, which of my columns are now going to be identical, and it turns out that A is going to be identical to BC, B is going to be identical to AC, and C is going to be identical to AB. So this is a quick way to do that. In the textbook, the notation for aliased effects looks like this. Note that the effect of A isn't just like A or BC. This is both of those effects combined. So if we assume that the two-way interactions are zero, then we're just left with A, B, and C, which makes sense. But if the interaction effect of BC is actually much larger than the main effect of A, then this gets confusing. And again, there's no way to tell which one we're looking at least there is a way to tell if we add a couple runs on here. But at least for now, there's no way to tell which of the effects we're looking at. So in this particular case, we kind of have to make an assumption that BC is zero, or do something else special. So the other way that we could look at this is kind of use the opposite of the defining relation here. So we could use negative ABC, and this gives different aliases. So if I do minus ABC, that's all the minus signs on ABC. That was the bottom half of that first table that we looked at. We could look at the different alias structure. So A times minus ABC is minus BC. So the opposite to the BC column is the A column. And if we go back, we can actually see this. In fact, I think I have my table still up on my chalkboard here. So what we're saying is that if we look at the opposite of ABC, so where all the minus signs are on ABC, and I apologize, my chart isn't as well put together. And then we look specifically at A and BC, that where these are crossing over, these should be the opposite. So here I see that A and BC are opposites. 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 So this appears like it's working how it should for this opposite relation that we have using this other defining relation. So both of the designs belong to the same family in the sense that both of them are using a defining relation of ABC. One's just positive, one's just negative. And again, if we combine these two, we get the full factorial through the sequential experimentation. Now, when we're looking at these, one thing that's an important vocabulary word to be aware of is called design resolution. Now, resolution looks at, if you think about resolution in a TV, it's like how small do the pixels get, how accurate does it get. In a resolution of a design, we're asking how bad is the confounding. So in this case, a resolution 3 design that says mixed effects are confounded with two-factor interaction effects, but no main effects are confounded with two-factor interaction effects, but no main effects are confounded with main effects. So the worst case scenario is going to be a main effect confounded with a two-factor interaction. So in this case, we have that 2 to the 3 minus 1. We denote the resolution of the design by the Roman numerals at the bottom of such a design. And again, the resolution 3 design indicates that the main effects at worst are compatible with a two-factor interaction. And you can count 1, 2, 3 in terms of an aliasing structure. So the number of letters in the aliasing structure can be helpful after everything's canceled out to help determine what resolution it is. Now these are always the lowest possible. So if I had a main effect confounded with a main effect, that would be a resolution 2 design. So even within the same idea, depending on the number of runs you pick, the defining relation, that gives you a different resolution of design. So picking the correct defining relation is actually really important to getting the best resolution you can. You want the resolution to be the highest number possible. So for a resolution 4 design, we would have 2 letters on the left and 2 letters on the right in our aliasing structure. This would be the smallest number of letters in any alias. Let me say that one more time. If I wrote out all of the possible aliases, that is, I took all of the effects, I multiplied it by the defining relation, and I looked at all of their aliases. A resolution 4 design says that the fewest letters that I have is 4 letters, and in this case, that would be a two-factor interaction with a two-factor interaction, or a main effects, an ME with a three-factor interaction, 1 letter, 3 letters. Both of those give me a resolution 4 design. So if this is the least amount of letters in an aliasing structure, then that's a resolution 4 design, and that's denoted here. Note that we can't have a resolution 4 design in a 2 to the 3 minus 1 study. So sometimes this is the best we can get. So resolution 3 for a 2 to the 3 minus 1 is the best we can get. Resolution 4 to a 2 to the 4 minus 1 is the best we can get. Resolution 5, where we have 2 letters on the left-hand side for a 2-way interaction, 3 letters on the right-hand side for a 3-way interaction. And again, after we've looked at all possible aliases of all possible factors and all possible interactions, this is the smallest number of letters on the left-hand side and the right-hand side. That's what gives us a resolution 5. Now you can easily make a resolution 4. That's a worse design. Resolution 4 would be worse than a resolution 5. Resolution 5 is the best you can get with a 2 to the 5 minus 1 fractional factorial design. You could make a resolution 4 design if you wanted to. Let's say you had a main effect aliased with a 3-way interaction. So that would be 1 letter on the left, 3 on the right. That would be a resolution 4 design. You could make a design like that. You could make an aliasing structure that would do that. That would not be as good, but you absolutely could. So note that the resolution comes from your aliasing structure, and depending on how you pick that defining relation, that can make these better or worse. One more thing I'll note on these, and I hope you've been taking good notes. If you haven't, rewind, take good notes on these. These are important. But one other thing I'll note, if you use the highest order interaction, so in a resolution 3, that's a 3-way interaction. In a 2 to the 3, that's 3 independent variables, and you're running half of that. That's a 3-way interaction. 2 to the 4, that's 4 independent variables. That's a 4-way interaction. 2 to the 5, that's 5 independent variables. A 5-way interaction. If you use the highest level interaction term as your defining relation, that will keep you at the highest resolution design in the 1/2 fractional factorial case. When you get into the 1/4 and the 1/8 fractional factorial cases, that doesn't necessarily work, but in the 1/2 it does. All right, so when we're designing these, again, I already told you the way that I design it. So for me, how I go about designing these is I look at my area where I'm going to be picking my defining relation, and if I want it to be the highest resolution, I'm going to pick the highest order interaction term I can. I'm going to look for all of the positives, and these are the runs that I'm going to keep. So anything with a positive here, that's a run that I'm going to keep, and this is the way in which I select my runs when I'm using a fractional factorial design. But this is not the only way that you can select runs, and in fact, though I find it easy to do quickly, these ways can handle more complex designs. So the other way that you can do this is you can start with your a full design we're going to do 3 minus 1. So you start with a full 2 to the 2 design. So you actually do 3 minus 1 equals 2, full 2 to the 2 design. And then you use your defining relation. Incidentally, this term over here can be called a word or a generator. So I use my defining relation, and I use this to construct what the third variable would be. So in this particular case, if I had A and B, C would be A times B. So again, I can just construct over here. If I had C, C times ABC would give me AB as my value. So in this particular case, AB, the interaction, is going to be all of my pluses and minuses for C. So I would literally do A times B. So my first value for C is a positive. A times B, my second value for C is a negative, and so on down the line. And this is how I could use this defining relation to generate my C value. And then once I had C, I could look at all the interaction terms, AB, AC, BC, and then ABC. Note that ABC is just going to be the same as the identity. AB is going to be confounded with C, AC is going to be confounded with B, and BC is going to be confounded with A. So looking at all those different terms, you could look at them, or you could use the theory to generate your alias structure and realize I don't need to make all those because I already have them here. So as you're looking at these, every fractional factorial contains the full factorial in fewer factors. So think about our projection. We're just looking at this from different sides, and the idea is that when we look at the k-1 original factors, we're just looking at this from a different perspective, but it really contains the whole thing. So it's like our flashlight is just coming from one dimension looking at the other two, but it still is looking at the whole full factorial design, just with those fewer factors being involved. So in this particular case, we'll try an example here. So we're going to be constructing a 2 to the 4 minus 1 design with the defining relation I equals ABCD. So what we would do is we would create that 2 to the 3rd design, ABC. So this is a full 2 to the k equals 3 design for ABC. And then we need our 4th variable because we want it to be 4 minus 1D. So we would look in this defining relation. We would say, okay, how do we get D? So D times ABCD, well, the D's would cancel, and I'd be left with D equals ABC. So the alias for D is the three-way interaction ABC. So to create each of my D values, I would go down the list, and I would multiply A, B, and C to get my value for D. So negative times a negative times a negative is a positive, positive times a negative times a negative is a positive, and so on. I'd multiply all three of these values, A, B, and C, and that gives me D. Now, the reason the main effects are important to get in our fractional factorial design is the main effects tell us what treatment combination we should be using. So previously, if you used my way, which is, again, I kind of like my way, it's longer. So in my way, I would have to write out the entire 2 to the 4 design, look at the highest order interaction, that ABCD, and then just find all the positives in ABCD and keep those particular rows. In this way, you don't have to write out that 2 to the 4, you actually write out the 2 to the 3, and then use the 2 to the 3 with the generator to create that 4th variable, and that can be, again, kind of handy. But the reason that you do this is so that you can figure out what your runs should actually be. So once I have A, B, C, and D, and remember this really is a 4-factor experiment, I want it to be 2 to the 4 minus 1. I want 4 factors, but I want to cut the number of runs in half. So I always had 4 factors. Always had 4 factors, even though I started with 3 and used the 3 to generate the 4th. I always knew I was going to have 4 factors. But the reason that I want to create the 4th main effect so bad is because that tells me what I should actually do when I'm doing my runs. So on my first run, it looks like all of these are negative. So I should do a low level of A, a low level of B, a low level of C, a low level of D. And remember, 1 indicates a low level of all the different variables. On the second run, I should do a high level of A, low BC, high level of D, and remember that's denoted AD. So the whole purpose of generating the main effects and using this method to solely generate this other main effect instead of writing out the whole matrix, first of all, is because a lot of these effects are confounded with one another. Note that something like AB would be aliased with CD in this case, and you can use that defining relation to determine that alias structure if you want to. So there are some things that aren't going to be confounded with these 4 that aren't listed here, but the 4 main effects are important to determine which treatment combinations we should be run. And remember, this is the whole goal. We are cutting out half of our runs. The goal is to figure out which half we should keep and which half we should do. So in this case, we started with our basic design of the 2 to the 3. We used the defining relation, which was set ahead of time, and again, for a 1/2 fractional factorial, that's the largest interaction between those 4 factors, to generate the alias structure so that we could create the 4th factor as a column. So that was our methods going on here. So again, our interpretation gets kind of wonky, and the biggest reason is because of the way in which the alias structure is created. So this factor effects estimate for A is actually A plus the 3-way interaction BCD. And so Occam's razor pretty much says that the simplest explanation is the best. So if we're looking at a 1-way main effect and a 3-way interaction effect, and we're trying to figure out what contributes to this number 19, Occam's razor would say, well, the main effect is the simplest explanation, so the main factor A is the primary contributor to this number 19, not the interaction effects. But this is a big assumption to be made. So it's important to acknowledge what assumptions you're making as you're interpreting a fractional factorial, because they are important to acknowledge. Note that down here, the 2-way interactions are all confounded or aliased with each other, and you can also note the resolution of this design. A is aliased with BCD, so I count the number of letters, 1, 2, 3, 4. B is aliased with ACD, I count the number of letters, 1, 2, 3, 4, and I count all of these down. I'm looking for the lowest number of letters that indicates the resolution. So if I had something like A being aliased with BC, that would be 3 letters. This would be resolution 3. But at no place do I have only 3 letters. I have at least 4 letters everywhere, so this is a resolution 4 design. The alternate fraction, you can flip this over, and again, if you did flip this over, what you would get is the full factorial design, which has a full definition of each one of these factors so that there is no aliasing. So looking at this, in determining different variables, this is just about the size of the different effects. So this Occam's razor assumption, there's some details on here. So it's important to realize that actually the main effects really do have most of the effect going on. They really are the biggest contribution of the different effects that we're going to be looking at. And that there are some visual ways in which we can explore these different values too. So if we wanted to predict a combination, we could actually use some regression ideas to calculate what our predicted point's going to be, even if it's not one that we actually ran. So note that if we didn't actually run this particular run, we could still use the effects that we've determined from our other values to try to make a prediction as to what that would be. And that's kind of cool to think about, that we can actually predict something that we haven't done before. All right, so in looking at this is a bit of a larger one, and I think in your textbook, well, I know your textbook at least has this. They might even have a bit of a larger one from here too. But this is a case where, again, my way, where I would write out the full 2 to the 5 design, I would look at the highest level interaction. So the defining relation here is I equals A, B, C, D, E. And then I would use that defining relation to pick which of the rows we would keep. That might not be feasible here just because it is so big. Here, using the textbook method where we use the 2 to the 5 minus 1, 2 to the 4 design, and then use that to generate the fifth factor would be important. Now remember, again, 2 to the 5 minus 1, k equals 5. At the start of this experiment, I have 5 variables. And think about gender, race, hair color, eye color, and t-shirt color you're wearing. I know that I want to look at all 5 of these factors at the very, very start of this study. So when I generate this full 2 to the 4 design, that is not because I was ever considering just running this with 4 factors. And it doesn't even matter which 4 factors I pick. It is just a tool to be used to construct this fifth factor in a way that uses half of the runs. So to be clear here, I don't want you to get confused. When we use this 2 to the 4, it's not that we were ever considering using a 2 to the 4 design. This is just a construction tool to be able to design this 2 to the 5 minus 1. We were always interested in all 5 of these factors. We just wanted to do it in half the runs. So to do the 2 to the 5 minus 1, again, I construct a 2 to the, I do the subtraction problem, 5 minus 1, 2 to the 4. I do the full 2 to the 4, and then I use the defining relation I equals A, B, C, D, E to calculate the aliasing structure of the fifth factor, E. I find the alias for E is A, B, C, D. And then I can use this calculation to just multiply A times B times C times D, and that gives me each of the values of E. And then I can use the A, B, C, D, E column to create which of the treatment combinations I should be running. So remember, anything that has a plus under it, that's when you include the letter. Anything that has a minus under it, you don't include the letter. And if we had anything with all minuses, we would just use the number 1. Now we would analyze this in a very similar way as we would analyze any of these designs. Now we would simply plug this into a software and let the software run its course. Now there is specific analysis software that you can use for the fractional factorial design to look at which of the factors is outstanding as something that's jumping out as a factor of interest. So in this case, we have x2, x1, and x3 jumping out as the big 3 factors of interest that we particularly care about, and maybe this interaction between factor 1 and factor 2, which would be aliased with the three-way interaction between 3, 4, and 5. And again, you can use that defining relation to help see that personally. But this is the goal, is to really look at, okay, so it looks like these 3 factors are really jumping out. X2 appears to be definitely the biggest factor that I care about. X1 and X3 definitely seem to be something to be considered, and this two-way interaction seems to be something that might be worthwhile. None of the rest of these seem particularly interesting. And again, we can construct these graphics in R. There are certain packages that are designed for this, but you could also just plug this type of design into an ANOVA with all your different effects. Now, it's important to recall that you're going to get some estimates, and in fact, you're going to be missing some estimates because some of these values are the exact same as each other. So using this defining relation, the 4-way interaction between A, B, C, and D is the exact same as the main effect of E. So it doesn't make sense to include both of these, and it's important to remember that a statistical test of E is actually a statistical test of the main effect of E plus the effect of the 4-way interaction ABCD. And the reason that we use that and interpret that as a statistical test of E is because of Occam's razor, implying that the 4-way interaction between A, B, C, and D is not particularly interesting. This has been our quick review of the 2 to the k fractional factorial design. This is going to close out our design of experiments class with this very, very interesting and useful design. We've only talked about doing a -1, so taking a 1/2 fractional factorial design, Please see your textbook to see some other types of designs where we would do a very similar thing. Probably the most interesting part of those designs is that instead of having a single defining relation, we have three defining relations. We would pick a second defining relation that we're interested in, and then we would multiply those two defining relations together to get the third defining relation, all of which would create aliases. So now instead of just every term having a single alias, it would have three aliases, one with each of those defining relations, and we would have to write all of those out for each of those terms. That would be for a 1/4 fractional factorial design, and of course for a 1/8 we would then do the entire process again, picking three aliases, multiplying all of them together to get all, or three defining relations, multiplying all of them together to get all of our 6 possible defining relations, and then we'd have 6 different aliases for any given term. So again, all that's in the textbook. I encourage you to check it out if it's something you're interested in. And that'll close us out for today.